Learning Outcome 8-9. Describe the difference between double sideband and single sideband modulation. With Learning Outcome 8-6, determine the spectrum for all signals in an amplitude modulation process. In Learning Outcome 8-7, we talked about how you could do frequency division multiplexing and thereby transmit multiple signals in the same space. And I talked about how these were wide, and therefore the number that you could fit in a certain amount of space was therefore limited. And spectrum is expensive, and a user buys the rights to use. So for instance, if we consider a spectrum that is band limited between negative omega m and positive omega m, it has to use a total of 2 omega m worth of band space. So as we fit all of these spectra into our space, if we have a limited number of kilohertz, for instance, worth of space in which to fit them, and that would be 2 pi x rads per second, how many channels or stations could you fit into that allocated frequency band? Well, if I gave you a value for x and then a value for omega m, you could calculate that. Now consider the fact that real signals, if in time everything's real, which most things we work with are, if we have a real signal, it will be even, thereby symmetric, in magnitude, and odd in phase. What this says is that if we know the lower sideband of our signal, we have all the information for the signal because it will tell you what is missing here. Likewise, if we have the upper sideband of our signal, we will then know what is missing right here because of that symmetry. And both of these signals only use omega m worth of band space. So now, if we go back to our problem of saying how many signals can we fit into a certain amount of bandwidth, if I were trying to fit one of these in instead, and these only have a width of omega m, now how many can we fit? Well, approximately twice as many. Not fully that many, because we need to leave a gap between them for practical issues. But we can certainly increase the number of channels, number of stations, and therefore the amount of data that we're transmitting in a fixed amount of bandwidth. This should sound like a good deal. So if we're going to do that, what do we need to do to this signal to get one of these out? Think about it. Pause the video, make a guess. Draw your guess on paper. Don't cheat. Make a guess. Well, we could apply a filter to block out half, or a filter on the other side to block out the other half. It's a good idea, but because this filter is not symmetric around 0, it's very hard to realize. Because remember, just like with signals, real filters will be even or symmetric in magnitude and odd in phase. And these two examples were not. So therefore, they're a little bit hard to realize. So we'll take a different approach. We'll take our signal, we'll do the modulation, and now we have our signal spread out, one copy at omega 1, one copy at negative omega 1. And now we will apply bandpass filters to chop off half of the spectrum or the other half of the spectrum, depending on whether we want the lower sideband or the upper sideband. So we don't quite get this, but we will get just half of our spectrum used because after modulation, we only have the half. And now we can take this, which occupies half the bandwidth, and we can transmit that. So we've transmitted it, we've received it. What do we have to do to it now to get our original one back? Again, pause the video, think about it. Put a guess on paper. You won't be marked off for credit if you don't do it right, but try a guess. What you should think about is that we want to take this triangle and locate it there, or that triangle and locate it there. If we were at the upper sideband signal, we'd like to take that triangle and locate it there, and that triangle and locate it there. How can we do that? That's shifting. And we can shift in both directions at once by modulating with a cosine. Okay, think again. What frequency would that cosine have to take? By how much do these signals have to shift? Omega 1. Negative omega 1 has to get to 0. Positive omega 1 has to get to 0. One's a positive, one's a negative, both are omega 1. Now, what does our spectrum look like after we've modulated? On a piece of paper, draw it out, shift this whole thing by positive omega 1, one of the impulses that goes with the spectrum of cosine, and then shift it to the other direction, negative omega 1, from the other impulse that goes with our cosine. If we shift it to the right, we should get that. If we shift it to the left, we should get that. Hey, look, there's our triangle that we wanted. What about for upper sideband? If we shift it to the right, positive omega 1, shift it to the left, negative omega 1, and again, we get our triangle. What would the amplitudes of these be? One over 2 pi, because multiplication in time is 1 over 2 pi convolution frequency. Pi, from the Fourier transform of the cosine, 1/2 from the original height of our modulated spectrum. Therefore, 1/4. Not quite the one that we wanted, but from here it's easy. Put a gain of 4 and then a low-pass filter. Okay, how about some practical issues? I was talking about using bandpass filters, and as I've drawn them, these are ideal bandpass filters. Therefore, we can get very sharp cutoffs in our spectrum. But ideal filters are really hard to build. So in general, we will not build an ideal one. We'll have a real one, and therefore there will be some transition band. For instance, possibly like that, or like that for the upper sideband filters. What does that do for a resulting spectrum? Well, we're going to have something that's not 1 multiplying it, something that's not 0 multiplying it. So it's going to get distorted. In this case, it would be linear times linear, which is quadratic. Linear times linear, which is quadratic. That looks really ugly. How are we going to get a triangle back from that? Well, the good news is that this little tiny bit here, if we did things right, will add in and fill in this space here when we do the modulation to reconstruct. And if we design these filters properly, we can fill in and get back what we're looking for. It does work, and this is used in practice. So let's review. We start from the beginning, the original signal in time, original spectrum. We modulate, send it through a bandpass filter, either a lower sideband or an upper sideband one. We'll return one of the sets of sidebands. That would then get transmitted. When we receive, we would do a regular modulation, which brings things back, send it through a low-pass filter to get rid of the sidebands, and then give it a gain of 4 to bring it back to 1. This first half of the process is called modulation, same as before, except for we have this bandpass filter included. Second half of the process is demodulation. Again, same as before, but we have a gain of 4 instead of a gain of 2. What type of demodulation is this? Got a cosine and a cosine. This is synchronous demodulation. Again, practice getting all the components, all the frequency pieces on each of these wires, and labeling all the frequencies on all of those components.